Calculating RC, resistive capacitive AC series circuits. All right, let's get going. We've got first thing, some information, 120 volt AC, 60 hertz, which gives me then, let's say a 30 ohm resistor. And the capacitor we're going to have is 650 microfarad capacitor. First step, sketch. Here's our source, resistor, capacitor. Items that we can calculate for the resistor: power, voltage, current, resistance. For the capacitor, VARs, voltage, current, XC. A capacitor is always considered to be pure, as in it never has any resistive properties to it, theoretically. In reality, it does have a little bit of resistance, but in any calculation that we do, we will always assume that the capacitor has no resistance. All right, over here, totals. That means total S, which is VA, total voltage in our circuit, total current in our circuit, total impedance, and total power factor. So we're going to do the same thing as the previous examples, where we're going to calculate all the values. We are then going to sketch them onto our Cartesian plane to show the relationship of the different phasors. So first step, there's my resistor, there is my capacitor. Let's fill in some of the values that we already know, which would be 120 volts AC, 30 ohms for the resistance, and then finally over here, the capacitance. We're going to have to calculate that with our 60 hertz of frequency. So remember, XC is equal to 1 over 2 pi FC. And remember, micro equals a relationship or a movement of the decimals 6 places, right? You're moving it 6 places to the left. So that means for us, 1 over 2 times pi times 60 times, well, 0.123456. Of course, there's other ways you can do this in your calculator also. You could just indicate it as an exponent, but I'm not getting into that here. 1 divided by bracket 2 times pi times 60 times 0.00065 farads, close bracket, equals 4.08 ohms. And what is that? That is XC, 4.08. All right, next step, we're going to work out the total impedance. The impedance value is a horizontal. So I'm going to say total Z is a horizontal, which is my resistance. But now, what about the vertical? The vertical goes down. It's in the opposite direction, like that. And this is my XC, 4.08 ohms. Total impedance. So, Pythagoras to the rescue, 30 squared plus 4.08 squared equals, take the square root of the whole thing, we get 30.276. $30.27. All right, so Z total 30.27. Now we can use Z total and E total to work out the total current. This would be Ohm's law. So that means 120 divided by 30.27 gives me 3.96 amps. 3.96 times 120. 475.71 VA. All right, let's work out the rest of the values for the circuit. I've got a current value of 3.96 amps, which means that if I take Ohm's law, 30 times 3.96 gives me 118.8 volts. 4.08 times 3.96 gives me 16.15 volts. And then I can calculate the power. I can either take the current, square it, multiply it by the ohms, or take the current and the voltage and multiply them. I'm going to take the current and the voltage and multiply them. 118.8 times 3.96, 470.44 watts. 3.96 times 16.15 gives me 63.95 VARs. So remember, we can have a total impedance triangle, and we can also have a total power triangle for our circuit. Total S, same thing, horizontal and vertical with a hypotenuse in between. The total Q of this circuit is 63.95. That's VARs, of course. And then the total watts, P, is 470.44. So Pythagoras is going to give us the total there in VA. So 63.95 squared plus 470.44 squared, square root the whole answer. We get 474.7, which is total S. Like every other time, I'm going to draw your attention here. I've calculated this value in two different methods. Because of that, they're slightly different. Is this a problem? No, it's not a problem. The more decimals you take, the less of a difference we will see, but that difference is so minor that we do not consider it relevant. All right, final step. Let's work out the power factor. Remember, it doesn't matter which of those two triangles we choose to use. Power factor is always the in-phase component divided by the total. In phase divided by the total. So I'm going to take the impedance triangle, well, the power triangle I'm going to take, 470.44 divided by 474.7. 0.99. That gives me a power factor of 0.99. Now, what is this circuit? It is not unity, which means it is not fully in phase. It is either lag or lead. When we're discussing capacitive circuits are always said to lead. What does this look like on a Cartesian plane? Well, the phasor diagram is going to be the same as what we have looked at in previous examples. We are going to have our current value, which is at the reference, and the current value for this particular arrangement is 3.96 amps. So closed arrow, I total equals 3.69 amps at 0 degrees. We are then going to have a voltage for the resistor. And the voltage for the resistor is quite large. It's 118.8 volts. So again, I'm not doing this to scale. So 118, this is V of my resistor, 118.8 volts at 0 degrees. And then we're going to have a voltage across our capacitor. The capacitor voltage, remember, when we're talking about capacitors, that the current and the voltage are not going to be in phase. And for our capacitor system, the current leads the voltage. And that means that the voltage for our capacitor is down here. I'm drawing a short phasor because we know that the voltage is only 16.15 volts. So this is V of the cap. I'm going to sketch it over here. V of the cap, which is 16.15 at 270 degrees. The capacitor will always be, when it's in a series circuit, the voltage will always be at 270 degrees. All right, what's the last one? Well, the last one is the voltage, right? Source voltage. So source voltage, this one we already know the magnitude, it's 120 volts AC. The angle we know is 0.99 power factor. So we can use the power factor, right? Just like in the previous examples. So the power factor is 0.99. And what that means is that we can take our inverse cos, right? We inverse cos 0.99, and this should give us an angle. Now remember, this is lead, isn't it? If it's lead, that means that we are under the horizontal. We are not above the horizontal. So when we're doing this calculation, when we get our calculator to spit out the inverse cos value, it is going to give us a value that says 8.1 degrees. Due to this being capacitive, it means negative 8.1 degrees. And that is because it is capacitive, right? Capacitive in value, so negative 8.1 degrees. So what is that angle? Well, we take 360 minus 8.1. 360 minus 8.1 gives me 351.9 degrees. So that means that my final voltage value here for the source is very close to 360. It's only off by about 10 degrees. So something like this. And that is E total. E total is equal to 120 volts at 351.9 degrees. The only tricky part about capacitance and capacitors in series RL circuits is that we have to remember it's leading. And so when we calculate this value, you need to keep this in mind that it is going to be a negative value from 0. Are there other ways to calculate this? Of course there are. I'm showing you the most straightforward. There are other methods that we can approach this with that would indicate a negative or a positive degree angle. But for this, I'm saying, let's keep it easy. If you understand that it is a leading circuit, ensure that you are subtracting that from 360 degrees and your arrow or your phasor ends up being below. That's all for our series AC RLC circuit example.